So, welcome back. In the first week, I'm going to repeat some of the same things which we discussed yesterday about practicalities. So I hope you don't get offended if I repeat some of the basic information where you can find lecture notes and everything. So the most important site is what we call the official University of Oslo website. And here you will find messages, typically weekly messages. So the same messages which I send by email via Canvas. You will find the same message displayed here. And you will typically get this towards the end of the weekend or the beginning of the week, so that you can actually plan what is going to happen on Wednesday, Thursday, and Friday. The lectures will also be, as I said yesterday, they're going to be recorded, and you should have the link available to the lectures from yesterday. So you can always revisit things if you want to, or if you don't have the possibility to be here in person because, something happens, you can always attend the lectures via Zoom. And if you cannot attend either the lecture in person or via Zoom, there's always a recording which you can look back at. I will also send, as I said yesterday, if you peep into the plan for the lectures, you will typically also find reading suggestions or reading recommendations. Now, the slides which I send, the link to the slides contain most of the things which I will say. But then the slides, they are they're meant to give you an overarching view of what is going to happen. They will contain code examples which are relevant for the projects and the exercises. But if you want to deepen your insights about a specific problem, the textbooks which we have selected, they should hopefully be of some help. And as I said yesterday, some of the textbooks tend to be weak on mathematics. Other ones have just mathematics and no algorithms, no codes, no nothing. So try to find a kind of middle way where you find what is relevant for you is possible if you just mix the different books here. So normally what I would recommend is the textbook by Aurélien Géron and the one by Goodfellow, Benjo, and Coville. These are the kind of basic textbooks. And the one by Goodfellow et al. Is actually one of the standard textbooks in deep learning. Now, there is, as you probably have seen, there are tons of textbooks out there. This is a field which moves at an extremely high speed. There are new algorithms, new ideas being presented on a daily basis. And there are zillions of people out there who actually deal with applications of machine learning algorithms or development of machine learning algorithms. There is an emerging field for those of you who are more mathematically inclined, which is called the mathematics of deep learning. So one of the nice things with this field, one of the things which I really like, being a novel field, there's a lot of space for creativity. And not all of the things which you see when you apply machine learning methods, not all of them are well explained mathematically. Sometimes you will hear statements like, well, this method functioned better than the other one. We don't know why, but we picked this method because it works better for our case. So sometimes you won't find a sound mathematical justification, but if that is something which triggers you, there is actually this evolving field which is called the mathematics of deep learning. And as in any new field, there's a lot of creativity, and there are actually many people applying this to basically all disciplines in science, in humanities, in social sciences, and so on. So it's an extremely rich field. Now, the thing which we also recommend everybody to do is actually go to the web, to the GitHub address of the course, and you'll find that a link to that one on the official UIO website for the course. And there you will find all the teaching material. It's freely available. Use that as your own material. Feel free to do that. there is a Jupyter book which summarizes or functions as a kind of lecture notes. If you spot errors, there have to be errors. I mean, when you write more than 100 lines, I mean, there have to be errors. I mean, none of us are monsters. And so if you spot errors, typographical errors, grammar, or errors in derivations, or things you think would be better, please do send me an email. I appreciate all the inputs. And the other thing is that we have this link here, which brings you directly to the weekly material. And that's the material which we will try to cover every week. Any questions about the practicalities? There's also, in the slides for this week, there's also a suggested deadline for the different projects. So just send me an email in case you see problems. So suppose we put a deadline for project 3, which collides with an exam, and many of you do take that course, then please let me know. And then we will try to be a little bit flexible and change deadlines. Okay, so let's go back to where we were yesterday. So yesterday we started with the derivation of the equations for linear regression, or what is normally called ordinary least squares. So I just want to quickly remind you of what we derived yesterday, and we're going to continue a little bit along this line and bring up some of the mathematics, and then we're going to look at some applications and discuss what the applications mean and how we get started with using linear regression. And then we are going to go back to some elements from statistics, because this course deals also with the statistical data analysis, and machine learning itself has a tight connection with statistics. You could say that this course, in addition to linear algebra, optimization problems, because we are minimizing some function, deals also with a statistical analysis of the data. So these are perhaps the three main ingredients which we are going to deal with. And I know that many of you, unfortunately, you have not taken a course in statistics. So how many of you have taken a course in statistics? At the University of Oslo, it's STK 1100 something? Oh, excellent. So this means that maybe for some of you, this may be boring, but we are going to link it up with the way we are going to make the interpretations here. So unfortunately, for many of the study programs, we haven't been able to sneak in due to space a proper course in statistics. Okay, so let me go back to the whiteboard. Sometimes it complains here. Huh? Okay. So you have to tilt this thing here. I didn't want to get there we are. That looks better. So let me quickly remind you of what we did yesterday. So what we did was actually to derive the equations for what is normally called ordinary least squares. Now, what we have, just to quickly remind you, so we are going to go do some repetitions in the beginning. So we have three basic ingredients in all machine learning methods, whether this is supervised or unsupervised, whether we are fitting a function, a continuous function, or whether we want to do a classification problem, whether we're doing clustering, or whatever kind of problems we are dealing, we will have our data. And typically here, we could have data which are organized in terms of vectors. So Y is something which we are going to call the output of a measurement, for instance, and X is the input. X doesn't need to be a vector. X could come in terms of a matrix. So if you have, for instance, data on the genetics of cancer patients, you may have a list of, let's say, 1,000 patients. So that would be the number N, which you see here. These will be the entries. And then these different types of tumors may have some features. So it could be the thickness, it could be the radius of the tumor, it could be the circumference or whatever. So these would typically be features which then would give rise to a matrix instead of a vector. Now, the next thing which you need is a model. Now, the data can be labeled or unlabeled. And often there's been a human who's been labeling the data. So the labeled data, which lead to supervised learning, is often, extracting the data is often an expensive process. Yeah, I should give you a digression here. Actually, in many of these face recognition algorithms, there was a slightly doubtful scientifically project from the American Defense Department, which dealt with figuring out what you wanted to do based on your facial expression. So there's been long-term research on connecting your facial expression with what you were thinking of doing. And that was in order to prevent specific actions. So this was a kind of research which involved people collecting photos of people and then try to label whether this person is happy, this person is angry, and if this person is angry, this person may do some malicious actions of things, whatever. Now, the labeling of all these photos, there were millions of photos which were then used in machine learning algorithms to train and figure out whether you could predict how a person would act according to your facial expression. These were labeled by people in different countries, and you know very well that in different countries, facial expressions may not mean the same, right? So, and obviously these were labeled by underpaid people. And all these things entered into this big machine learning algorithm. Now, this project is no longer funded by the Defense Ministry in the US. So there was a lot of criticism in terms of this not being scientifically sound, because, I mean, to link your inner feelings with your facial expression is not something which I don't think that's very trivial. But that's an example of tons of data which are labeled by humans. And clearly that introduces quite some error. So labeling the data can be something expensive. Now then, when we have the data, we need a model. And when we do linear regression and derive the standard ordinary least squares equations, the assumption we make is that there is a function, f, a continuous function that exists. We don't know it. And then there is a normally distributed noise. The assumption we would then make, so in our case, we are going to use this quantities labeled with a tilde as our model, and we are going to approximate that with a polynomial of some degree. That's just one possible model. You don't need a standard polynomial. You could think of functions like sine or cosine or other types of functions which you use to parameterize your data. Then, when you have this model, what we did was actually to set up the problem in terms of a matrix times a vector. So the unknown quantity are the quantities beta, which you see here, which then are the different coefficients in front of the polynomial terms. So beta 0 would be the intercept, beta 1 is the slope, then beta 2 is related to x squared, and so on. So this is just a pretty simple model. And then we have a vector beta, and we have this matrix. And the reason why I bring this up again is that I want to have you with me in the kind of naming. So this matrix is normally called a predictor matrix. It's called a feature matrix, a design matrix, because it gives you a design of the model. So in our case, every column represents a feature. And in this specific case, a column represents the degree of the polynomial. And the matrix X, in this specific case, is now a matrix which then reflects the values of the different polynomial terms, and everything in the matrix X is well known. So unless the data have been produced by random variables, or there's some randomness in it, this matrix is deterministic. So this brings, as an aside, to what is going to come when we are going to discuss a statistical interpretation. This matrix X is going to be given by deterministic quantities. There's nothing statistical in it. So you could think of you running an experiment and you have a beam with particles. I mean, I do subatomic physics, and this beam of particles has fixed energies, which you determine. So there's nothing stochastic in it. So the matrix X is often seen as a non-stochastic quantity, because often you are the one who controls the input to the data, to the experiment which you do, or the way you collect the data. Not okay? So this is going to have important consequences later when we are going to introduce some statistics and we're going to look at expectation values. So you can think of these, even if I generated by the random number generator, as numbers which are not stochastic. Then we have a model which is now given by this matrix X, which is well known, and then we have beta, which contains the unknown parameters. Then what we know then, what we want to do then, is actually try to find these parameters, and these parameters are determined so that they optimize the quality of our model. So we want to have a model which reproduces the data. And clearly that means that we need to deal with some optimization. That's where we have the optimization part in machine learning. And then when you have this defined, what kind of function you want to deal with, you have to cook up a kind of optimization algorithm. And in our case, the optimization is pretty simple. It's actually calculating the derivative of this quantity with respect to the parameters beta. And then we just want to put that one to zero. And that means that we have to calculate gradients. There are many ways of doing that, as we discussed yesterday, but one of the simplest one, which we always end up using in many applications, is the mean squared error. Now, the mean squared error puts also emphasis on outliers. So if you have a poor model, you will actually get a large mean squared error, as we saw yesterday in a simple application of the library scikit-learn. Then, when we rewrote this, we could actually rewrite this term, or this mean squared error, in terms of a matrix vector relation. So we have a much more compact expression, which is this expression here. And where we ended then was actually me giving you the derivatives of this expression. And then we had the expression, an analytical expression for the parameters beta. Now, one of the things which I wanted to do now is to have a kind of mathematical intermezzo and just look at how we calculate derivatives of matrices. So you can, and one of the exercises next week, you partly have the solution in the slides, is actually to take the derivative of this quantity with respect to beta. So if you look at the expression which we have here, this one, you will simply calculate the derivative with respect to beta j. Now, you can actually do that term by term for every beta j, and just write out the different lines which you get for every beta j by taking this derivative, and that's not very difficult. Or you can just use formula for the derivatives of the vectors, calculating the gradients of vectors and matrices. So I just want to give you some of these expressions because you would find them useful later on when we are also going to calculate derivatives of more complicated cost functions. But then in those occasions, we would typically use software like automatic differentiation. So what I'm just going to give you as a quick reminder on these things, the thing which is important as well, and I'm just going to mention that before we move on, is actually about the dimensionality of this problem, which you see here. So let me switch notebook to today. So let's get started here. So what we had is an expression for the optimal parameters, which are given by what we call an analytical expression. You obviously have to calculate it numerically, where we have this matrix X, we have the transpose of it, and then we have the data. So everything which you have here is known in terms of the inputs, the model you have opted for, and the output data. So if you now look at the dimensionalities of these problems here, so we know that beta, just to remind you, contains a given number of features, and this contains a number of features D. Then Y, our output vector, contains a set of variables with length n. We're assuming these are real numbers. And then the matrix X is assumed to be a matrix then of dimensionality, where the rows, and I'm going to use this definition where let the rows indicate the entries. So if you have a list of patients and these patients have suppose well, I shouldn't go back to tumors. Let's take another example. We have the example with a credit card debt, whether people pay their credit card debt or not. And then you would have a number of credit card customers, let's say 10,000. And then you would have a given number of features which you use to classify these credit card holders. So this could be age, education, married, not married, and so on. And then based on these features, you can make a predictions whether this person would pay her or his credit card debt or not. So typically if you're a student, I mean, there's a lower threshold for what you can pay, and then there's a higher likelihood that you may not pay your credit card debt on time, and so on. So this matrix, the way we are going to organize it here is to have the entries, or that means the observations you make, and then have in the columns, we would have the number of features which characterize. And in our case, the number of features for this simple example is actually the polynomial degrees. And then you see now that when you look at the matrix you have to invert, if you look at that matrix, this is actually a matrix of dimensionality D times D. If you take the transpose, then the matrix is a matrix of dimensionality D times N. You multiply that with a matrix of N times D, so this becomes a matrix of D times D. Now there's a reason why I bring this up. So the method which you see looks extremely nice, but you have to ask yourself, when can I use it? What are the limits of this method? The typical situation which you encounter is a situation where D is much, much smaller than N. So typically, if you're now fitting a polynomial, you could have N equal to, you could have 10,000 data points. And then you could have a polynomial of degree, let's say 10. So the matrix X is a matrix which is 10,000 times 10. So it's pretty large, but not too large. But then the matrix you want to invert is just a matrix which is 10 times 10. To invert a 10 times 10 matrix is a kind of baby case in linear algebra. So that's something which you do easily, and the limit for these kind of methods arise when you're getting into, let's say, 100,000 to 1 million. So we split between what are called direct methods, where you can store the matrix on RAM and then perform the calculations and perform the matrix inversion, or when you have larger dimensionalities where you need to use iterative methods. So if you're doing cancer research, you may have n equal 1,000 patients, but then if you want to retrace which parts of the DNA are responsible for this type of tumor, you may have millions of features. So this D may be equal to 1,000,000, but N is only equal to 1,000. Then clearly these kind of methods are methods which you cannot implement easily. So you have to keep this in mind. So linear regression or matrix methods like this one, they work extremely well when you have much less features than you have a number of entries. And typically, if you have 1,000 points, you would not fit a 1,000th order polynomial. So suppose these 1,000 points are generated by a second order polynomial, you wouldn't fit a 1,000th order polynomial to reproduce a second order polynomial, right? So clearly, this dimensionality problems is something we need to keep in mind when we are using the different methods. For most of the cases we will encounter, these methods will have matrices which are not very large. We won't have that many features. This becomes important in particular, I'm mentioning these all kind of side tracks here, it becomes extremely important when we are calculating gradients. So if the gradient is actually proportional to this matrix X in many cases, and when we use a method like Newton-Raphson, does that ring a bell? That's an iterative method to find the roots of a function. Ideally, we would actually need the second derivative. And for linear regression, the second derivative is actually going to be almost equal to this matrix X transpose times X. And if to calculate the second derivative, if we have a huge matrix, becomes almost impossible. So the dimensionality of the problem is something I want you to think of. We tend to forget it when we deal with projects because then we want to solve the problem. And suddenly something strange happens. Our machine just doesn't do anything more, it just locks. And that's simply because you're running out of memory often. So these are small things, but they are important things. Now, the thing I wanted to add, in addition to this, is a small reminder on derivatives of or gradients of vectors and matrices, because that's something which we will need as a mathematical tool. So let's take this digression and let's now look at let's derivatives. Let's just call it derivatives of gradients. So suppose we have a function f, and this function, now I'm just going to indicate it, it depends on a vector x. This is the typical function which we had in the beginning here. So we have a function with outputs, which then depend on a vector x, and I'm going to put arrow on it just to indicate that these are vectors. So x1 down to some xn minus 1. So we say this is an element in n here. Then if I take the gradient of f, grad f, which we also write like this is going to be given by a d partial derivative. I'm writing x, and then with respect to x0, and this goes down all the way to xn minus 1. So I hope this looks obvious, pretty obvious. Now we can have a function, however, yeah? Oh, yeah, yeah. Yeah. Does it vanish here as well? Oh, yeah, yeah. Thanks. You're right. I have to think of that. Thanks. Okay, so we can have a multi-valued function. And in that case, I'm going to write this with a vector on top of it. And this would be a function now which is given by several functions. On x, there's a function f1 of x. So x is the same vector as before. And down to some f of mn minus 1 of x. So this function now has, this vector here has actually length n. Now, when we are calculating the gradient of that one, this leads to a famous matrix, and you may have seen that one. Does anyone remember the name of this matrix which you get when you take the derivative of a function, which now is a function of many functions? Yeah? The Jacobi matrix. So let me just bring it up again for you. So this would be a matrix which looks like this. So we would have a d of f of x, and then I would have a dx0, and this goes all the way down with respect to x0. So I would have an fm minus 1, and now I'm skipping this dependence on x in f, and then I would have an x0, and this goes on, and the matrix is a d of fx. Let me just skip the dependence on x here, just to save space. And then a d of xn minus 1. And this goes down all the way to d of fn minus 1 of d of xn minus 1. And this is called the Jacobi matrix, and it's often just written in terms of a J. And this is a matrix now of dimensionality m times n. And the matrix elements, if you look at them, a matrix element Jij is then equal to a d of f of I of d of x of j. So a typical example which you will need. So in one of the exercises next week, we actually want you to use the expressions for the derivatives of matrices and vectors to derive the ordinary least squares, which I did here. And one of the examples we can look at now is a case which is pretty common here. So we have, suppose we have f of x is given in terms of a matrix A of x. A and x is a vector. So A is a matrix. And let's just say that the matrix has dimensionality m times n. Then we assume that x has dimensionality or length n, and that means that f of x has length m. Then we can rewrite this in terms of the specific index f of I. So this is one of the terms of x, and this is now given by j equals 0 up to n minus 1. And then we have the specific matrix element. So I'm going to use uppercase letters for matrices. So that's a notation I'm going to use throughout the semester. And then I'm going to use lowercase letters for vectors and lowercase letters for matrix elements. So that means that I would have an A00, A01, and A0n minus 1, and then an minus 1, 0, and then at the end, minus 1, n minus 1, like this. So that means that I can rewrite this as an A of ij multiplied with xj. And this would just be this element f of I. Then we would like to calculate derivatives, and the typical derivative which we need then in this specific case could be, suppose we need that f of I of x of j. So if you look at the definition, what would that look like? Anyone who sees that on the fly? So you have the definition up here. So we have the definition of the quantity a times x. And now we want to take the derivative of f with respect to xj. Yeah? Aij. So this will be one of the things you would need to solve one of the exercises next week. So this is just a plain paper and pencil exercise. This is just to remind you of the way we actually write out many of these expressions and how we actually can compute the derivatives. Now, what I'm going to give you is also a set of expressions which you would find useful. So this is not a course in linear algebra, but I wanted to give you a list of useful expressions. Useful expressions, which you will encounter again and again. And in the lecture notes, you will actually find more. So if we take the derivative of the two vectors, we have a vector transposed multiplied with a vector, and the derivative with respect to x, this is given by the A transposed. So try to do these calculations yourself. So write down the mathematical expression for the inner product of two vectors, x transposed times A. Just write out the expression like I did here, and then calculate the derivatives. So that's the way you would actually proceed in order to finding these derivatives. Now, I told you that calculating derivatives is something which we don't need to stress that much with, but I wanted to have you with me when we are deriving these equations for ordinary least squares, because it's useful to have seen these things. But else, in all actual implementations, many of you are going to use automatic differentiation. So automatic differentiation is painless differentiation. So that saves a lot of time, because doing this kind of operations, which I'm doing now, it's okay, but it doesn't give you any deeper insight about the problem which you're looking at. But it's useful to actually have seen how we derive these equations. So I hope you don't mind if I just remind you of some of these things here. Okay, so we have other relations which we will use. So we can have AT times X times a vector B, and then I take the derivative with respect to vector X. So when I don't put arrows, I hope you see from the context that these are not scalars, these are actually vectors. And this is equal to A of B of T. Then there is another very useful relation. We have X transpose multiplied with a matrix B. So remember that matrices are uppercase, given by uppercase letters. Then I have a D of X. And this is actually given by X of T of B plus B of T. Now, this relation actually is very useful when you are going to find derivatives of quantities which we want to optimize, because many of the quantities will actually come out like a vector transposed times a matrix times a vector. And then we need to take the derivative of that in an optimization. So this is a very useful equation which you will actually encounter many, many times. Now, another expression which I'm going to give you is the one which I used to calculate the derivative in ordinary least squares to get the equations which you saw. And if you now look at the more general form for it, so we have a vector X, a matrix A, and then we have a vector S, which is actually the parameters beta, if you replace it with those. Then you can have a matrix W, so which we only requirement is that that matrix is symmetric. And then we have X minus A of S. So the requirement is that this matrix is symmetric. Now, if you then take W equal to the identity matrix, so just to remind you of that one, it's ones along the diagonal. If I do that, then I have just X minus A of S transpose times X minus A of S. So this is just a small digression here. Let's just put that in. And what we had was 1 over n y minus X times beta transpose y minus X times beta. This was the expression which we wrote in a compact vector matrix form for the mean squared error. And you see now that if you put this matrix W equal to the identity matrix, then if I take the derivative of this quantity, so let's just bring that one down here, I just bring this up to show the analogy here. This is actually equal to minus 2 times x minus a times s, the transpose, times this matrix W times the matrix A. And this is the expression you're actually going to play around with next week when you do the paper and pencil. There will be, in the beginning, paper and pencil exercises as well. Any questions so far? There's going to be another exercise next week. And if we look back at the mean squared error, there's a very important quantity here. So what we found for the mean squared error, which we have written as 1 over n of y minus x times beta, t y minus x times beta, and we call this for function c of y given beta and x. I'm just going to use a shorthand. We just c of beta here. Now we calculated, yesterday we calculated the derivative of this quantity, but another quantity which is equally interesting is actually the derivative of c of beta, the second derivative. So we're going to, since this is a derivative, second derivative, what we are going to show in an exercise next week. So this is something I want you to see actually, because it's a pretty important thing. It's a 2 over n, and this is very interesting actually. And I'm going to tell you why this is interesting. So this is a second derivative of a matrix. So you may not see the connection immediately, but let's now assume this is a second derivative of a one-dimensional function. So let's suppose now that the one-dimensional function we have, this c, looks like this. So we have c of beta, and it goes like that. And here we have the beta optimal. You will basically just see me making at most two-dimensional plots. When I'm out of one dimension, according to my wife, I am really shaking ground. She thinks of me like a one-dimensional person. So 2 dimensions, when you see this graph here, this is perhaps some of the best things I can draw here. Eh? So forgive me for the quality here. So this is the function we want to optimize, right? What kind of function is this? It has a name, right? When it has a minimum. By the way, there was a fly here. That's the one which moves my brain, actually. It just escaped. Yeah. That's a convex function. So it has a minimum. It has a global minimum here, just one minimum. Now, to have cases like this is very seldom in machine learning. So often you have complicated functions, and you may have tons of local minima, and you may be stuck in local minima. So this is a convex function. What does that mean for the second derivative? So if I take d of c of d beta, since it's a scalar, what kind of value does the second derivative take? Less than 0, larger, equal to 0? Anyone remembers that? Yeah? Yes. So if the curvature, as we call it, the second derivative, if this is larger than 0, then this is convex. Now, with a matrix, and this depends on whether you've had a course in advanced linear algebra, you can actually see from the matrix whether this will lead to a global minimum or not. So the matrix which you see here, this specific matrix, and then we're going to take a break after that, this specific matrix needs to have some properties. It's a property on the eigenvalues. So anyone who has encountered these kind of matrices? Yeah? Yes. The eigenvalues have to be positive, and the matrix has a name. Positive definite. So if you have a matrix, and actually for ordinary least squares, the matrix is positive definite, and I invite you to check that. So ordinary least squares is one of these gentle problems in optimization. So the matrix is positive definite, and when the matrix is positive definite, and you can relate that one to the curvature and optimization problems, that means that you will have a global minimum. So that's a theorem in optimization theory, which we are not going to prove. And that's a very useful property. Now, I'm mentioning this because you saw that in linear regression, there are some nice things here actually. So I need to just steal 1 more minute before we take a break. If you look at the expression here for the second derivative, so this one, and then you go back to ordinary least squares, what you have is the same matrix appears here. Now, this matrix is going to pop up in another occasion as well. This matrix, which you see here, X transpose times X, is going to be proportional to the variance of the parameters beta. So that means that we can estimate when we have the variance, we can take the standard deviation, and then we can put an error on the parameters which we have defined. So you would have an error in your model. And that's very, very important when we are going to assess the quality of a model, to have the error on the parameters. So this fly really wants to get back into my brain, eh? So this was just a side thing, but these are important things which you will see again and again. So this matrix is, and ordinary squares is actually one of these examples where we get nice, neat analytical expressions for complicated quantities later on. That's also why linear regression is often used in all machine learning courses as a kind of introduction to machine learning, because we have in many cases nice analytical expressions. Okay, I'm going to stop now, I promise. So I'll stop the recording, and then So before we move on to some applications, I just wanted to show you one specific case here. And I also forgot to mention one thing, and thanks to people in the audience here, this calculation and this relation with the convexivity and the global minimum, that implies that this matrix X transpose times X can be inverted. So I didn't say that, but I was assuming that implicitly. So next week, we are actually going to look at what happens when this matrix actually has columns which depend upon each other. And then we will have problems with finding the inverse. So that's a very important aspect of many of these methods. Okay, so I just wanted to show you a very simple example. And I guess most of you can actually imagine what will happen if I now assume, so suppose now as a small example, and this is often very useful when you want to check your programs. So suppose now that xt times x is equal to the identity matrix. And then the question is, what is the cost function, which in our case is the mean squared error? So let me just bring that up for you. So we have assumed now, so let me bring up the cost function, which we have defined here in terms of matrices. So it's 1 over n, matrices and vectors, x times beta transpose times y minus x times beta. And then what we have is that the beta optimal is given by the inverse of this matrix times x transpose times y. Now, what happens if we now have this extremely simple case where the matrix which we have set up, which contains our input variables, when it's transposed times x is equal to the identity matrix. Can you see that on the fly, what will happen with the mean squared error? So it achieves a very special value. So this value is normally close to what Norway gets when they try to qualify for the World Cup in soccer. The number of points, 0, exactly. If you plug it in, you will see that this is exactly equal to 0. This is a very useful test. When if you're a little bit unsure whether your calculations are going wrong, then it's useful to actually plug in that tester. So what you will get then this is I'm actually going to use that a little bit later in demonstrations of something which is called ridge and lasso regression, because then we're actually adding complications to the standard ordinary least squares. Any questions so far? Okay, so what I wanted to do is actually to give you some exercise, some simple examples and demonstration of what we can do with ordinary least squares. And if we then go back, what we need to do then is actually go back a little bit to the Jupyter notebook. So let's bring that up again. So when you go to the weekly material, you have a Jupyter notebook here, and that's the one which I'm going to run. And you saw parts of it yesterday. And I'm actually going to go down a little bit and show you. So I'm going to scroll down to some of the material here. So this example, I mean, you can actually run some of these examples and take a look yourself. But before I do that, I actually wanted to give you a quick reminder of the motivations behind using linear regression and ordinary least squares. So you can see some of these points, and that perhaps helps in seeing why ordinary least squares and these type of methods are parts of the machine learning family. So some of the things we are actually going to look at next week is to calculate the variance and link this with statistical properties like mean values, variances, and we are going to derive the same equation taking an approach where we assume that the output y is distributed according to a Gaussian distribution. If we do that, we can actually derive exactly the same equations which we did now for the parameters beta. And that's extremely useful because we don't need to think of linear algebra all the time, but we can actually link it with a statistical interpretation. And that's extremely useful. And we will come back to this. You can also find the standard error or the standard deviation for the parameters beta of your model. And that means that when you make a fit to the data, then you can actually provide an error estimate of your values. Then it's easy to introduce other things like something. Have you guys heard of something which is called the bias variance trade-off? This is a recurring theme in machine learning, and this is something we will discuss a little bit later. And then it's easy to code, as you can see. It allows for easy hands-on understanding of gradient methods because we have an analytical expression for the gradient. So when you are implementing, let's say, automatic differentiation, and you're a little bit unsure whether that functions properly, you can actually compare what automatic differentiation gives compared with your analytical expressions. When you're going to write your own code for stochastic gradient descent, which is one of the standard methods, you can compare that with the analytical answers. So there are many, pros when it comes to linear regression and as a kind of way to get started with thinking about machine learning and more complicated machine learning algorithms. And then the thing which I wanted to go through a little bit here is about some of the data here. So I also wanted to mention, you should feel free to take the codes which you see here, if you like them, obviously. I mean, I tend to program in lectures in a very simple way. Some people say that I'm too much influenced by old-fashioned Fortran, but I try to keep the codes as simple as possible, not have too many fancy things. But the code which you see here allows you to define paths. So I like to place the results in a folder, figures in a folder. So normally I generate figures and so on. And here there's a data set, the data set which I mentioned yesterday, this evaluation of masses. And what I've done here, I've been using pandas to read in, and this is what we discussed yesterday. And I'm sorting everything by A, which is a number of protons cross neutrons. So this is, I hope you can forgive me for taking this specific path. This is just an example. You can replace this example with other types of examples. Now, the thing which is interesting to see then is the way you actually construct the design matrix. So I decide now that I want to fit this matrix with a polynomial which is not like a standard polynomial you've seen, but it has an intercept, it has a linear term, and then it has a term which goes like this term to the power of 2/3, power of -1/3, and power of -1. So this is related to the physics understanding of this problem. And what I'm doing now, I'm simply printing out the design matrix for the data I've chosen in the fit, which I want to do. And this is something which is always useful to actually plot or print the design matrix, just to see that things are going correctly. So this is me now making a model for fitting this data. So the data is given by these binding energies as a function of this number A. And this number A is something which, when I use pandas, because this table had something like, I think, 20, 30 columns with inputs. I don't remember exactly. And then what I'm doing now, I'm actually grouping the data by this array A. And that means that when I'm now setting up my design matrix, I'm actually going to let that one determine the way I set up the model. So it's the energy as a function of this variable A. And then I have a model which is guided by the physics inside. If you're dealing with a model from geophysics or from chemistry or from any other field, you would have different types of setting up the design matrix. But it shows you a little bit how easy you can use pandas, read in the data, and actually get started. So this is an example of you making the design matrix, right? And you have to bake in some model. You have to decide what the model should look like. Now, when we come to neural networks, it's going to be a little bit different because, well, you may be tempted to feed in a model like that to a neural network, but that would defy what a neural network is. Because in a neural network, it's a network which finds the right parameterization. You can guide the network, but then the network will be biased by how you guide it. So there are many small, how to say, almost philosophical questions which will pop up as we move on, and how we deal with a model. So constructing a model is actually one of the more difficult things. So this is what we have been deriving, and you can see in one of the exercises, you can actually, when you're going to show the equation here, then you could actually just take element by element like this, or you could use these relations for derivations of vectors and matrices which I gave you, and just show that you get the same relations which are set up here. So I'm going to, and you can see the useful matrix relations here. I'm going to say something about you setting up your own code. So if you want to write your own code here, you have to read in the data. You have to define the design matrix, because that is your model. So when you have done that, then you can now decide upon which method you want to use. So if you're typically dealing with a polynomial approximation, normally there is no problem with matrix inversion. And the simplest way then is just to write this matrix beta, which we have here, this vector beta, and via the matrix inversion algorithm, which you have in the linear algebra package in NumPy. And here you see you take x dot times x, you invert the matrix, and then in my case y is given by these energies, and then my model y tilde is x times beta, and that's my model. So so this produces my parameters beta. That's the way you would actually write your own implementation of ordinary least squares, unless, and I guess you guys have tons of spare time, you want to write your own function for matrix inversion. It's actually not that difficult. I guess spare time is not exactly what you have a lot of, right? I will try not to abuse on your time. I hope not. Okay, so you can run that one. Alternatively, NumPy has a functionality which does the least square for you. That's another option. And then you would use the fit function here. But this is the way you would actually implement everything here. And then you can run it, and then just run this one, and then you can see the quality of the fit which was made here. Actually, the fit which I'm making, or the model which I'm setting up, is not the best possible model. I should also have a dependence on the number of neutrons and protons, if there is somebody here who's more familiar with subnuclear physics. But this is typically the kind of the quality of the fit. And the thing which you can do as well is to produce the mean squared errors. So an R2 score is one of the scores which you would do, and we haven't talked much about that. So ideally the R2 score should be equal to 1. You can write your own function for the mean squared error if you want to. And you see that in this case, the fit which I made, so this mean squared error function which I wrote, that takes in the data which we have, and it takes the model. So this will be my prediction, and this will be the data set. And in this particular case, you see now that when I take the energies which I have read from this file, and then plug in my prediction, then I get a mean squared error which is on the order of 0.02, which is okay. So this is a typical kind of assessment you would make after you've been performing the fit. And then clearly you can ask yourself, can I improve the model? Can I add more insight into the model and make it better and better? So these are things which are extremely useful to look at, and which you will have to include when you are analyzing your data and studying your model. So for project number 1, you're going to study the quality of the fit as a function of polynomial degree. So you're going to fit a function which is actually a 2-dimensional exponential. And then clearly that means that you can have an infinite order polynomial, as you know, when you look at the Taylor expansion of an exponential. And then you have to decide when you stop. So that's a typical example where you would provide the mean squared error and see how things develop. Now, there's one thing which we haven't discussed yet. Well, you can also produce the relative error. So below here, there are actually inputs like the chi-square function, which is also very much used. This relies on you having the variance. It's something you would often use when you have experimental data with a standard deviation on the data points. I just invite you to take a look at it. So I'm not covering everything which is in the weekly slides. So some of it can be seen as just reading material. And also the other thing I invite you to take a look at, if you look at the calculations here, if you just have a linear fit, you can actually find analytical expressions for the fitting parameters. So this is just you manipulating with some terms in the mean squared error. So that's also a useful test of your codes, whether if you do a standard first order polynomial fit, you actually can get analytical expressions for the parameters. So that's also a useful thing to look at. Now, there's something, this is another CVS file, and this is a comma-separated file, and I'm just going to run it first, and then I'm going to say something about it. And there's something which I want to talk about in this connection here. And this is a very important aspect in machine learning, so we're going to introduce that immediately. So one of the things you would typically do is to split your data in training, validation, and test data. Often you just split it in training and test. Why should you do that? Why don't we use everything for training? Let me see a little bit. Yeah, we can take the one over there. Yeah. Yeah. So you can make a model which is a perfect fit. Okay? What happens then if I use this perfect fit to the data and apply to something which hasn't been included in the training? Yeah. You may actually fail miserably in reproducing the data which was not included. So this is an important thing which leads to topics like overfitting and underfitting. And overfitting is a problem which is very easy to reach, and it's difficult to prevent. So these are things which we are going to discuss a little bit more in detail next week and the week thereafter, and how we can actually alleviate the problem of overfitting. So to show you an example of overfitting, I'm actually going to run a calculation with a machine learning algorithm we are going to see later, which is called decision trees. And decision trees can actually allow you to make a fit where you actually go through every single data point. And if you do that, you have a perfect fit. You will get a root mean squared error, which is close to zero or zero. But then if you have a point which is just an outlier, you would then typically fail miserably with your prediction. So remember again that machine learning, the traditional way we do machine learning, is actually to allow you to make predictions. And clearly you train it on data, and if the prediction is a bad one, then you would say that you haven't reached a good model. So I just wanted to show you an example of that by actually going back to this example with the nuclear binding energies. So I'm using that one because it allows me to catch many birds with a stone here. So let me just run it, and then run the first cases. So this is just a repeat of what we saw. So this is my linear fit. But now there is a model which is called, or an algorithm which is called decision trees. So decision trees is actually based upon the game which many of you probably played with your parents when you were on a long car drive. Has everybody played these 20 question games? Somebody thinks about something and the other ones have to guess it, and then you have 20 questions, and then you just nail it down till you hit the answer. So decision trees are essentially like that. So you can really narrow down a decision tree in the depth. So the depth would be the number of questions which you were allowed to ask in order to make to guess what that other person had been thinking of. So one of the parameters you would have in a decision tree is what's called a depth. So in this case, we're actually fitting the same data by allowing you to ask up to a depth of 9, which you could think of almost asking 9 questions. It's not exactly that, but you can think of a parallel to that. And what you will see now is that the case where you've actually, so the case here, which is called regression 3 here, is the case which gets closer. So the max depth, this line, is the one which really follows the data here. Now, what I could do, so if I could just take away some of these plots here. So let me just take away the max depth 5 and that one so that we just see one of them. See a little bit better here. And you see now you're basically on top of the data. One thing you will notice, so this is the data and this is the prediction. You see now that you are just bang on here. So that means that you have narrowed down the reproduction of the data to the exact data point. So the prediction you make is the average of the number of points you put in the smallest region, which you decide. So if you have 5 points, your prediction will be the average of 5 points. Here we are actually down to one single point. So if I increase, or no, decrease, suppose now I just do 3 here. What you will see then is not a as good fit as we had previously. And you will also see that my prediction has, sometimes it has a lot of same values, if you see this. So this is the average of the amount of variables in a small region which you have defined. So this model, this algorithm here can allow you to really make a perfect fit to the training data. But then if you add a point outside the training data, you will make most likely a very bad prediction. Okay? So this is an example of overfitting. So you've tuned the model to all the training data. So what is done then, and this is an important thing when you're dealing with machine learning algorithms, if we now go back to this splitting of data in train and test set, and the thing which you would do then is actually to, and there is no kind of golden rule for how much data you should put in training and how much in test. And we are going to see later that there are techniques by which we can improve the quality of the model by resampling. So this is something called resampling techniques. But what you would typically do is that you take 70 to 80% of the data and use that for training. So you can select this randomly, and then the rest of the data would be test data, which is untouched. This is the simplest approach which is normally used. And this is something which hopefully hinders or reduces the problem of overfitting. Now, how much to take is something which you have to play around with. Now, if you have, if you're doing theory calculations, you can often generate the data on the fly. So then there is no problem. Then you can use all the data to train. And if you're using the same model to generate some new test data, there is no problem. But normally, the data you have are the data you have. So the data can be a result of a survey which has gone on for 30 years. And there is no way you will wait another 30 years before you make the data analysis to collect new data. So in many cases, the data from experiments, they are the data you have. And the quality of the data is what you have. If you run an experiment at CERN, it runs for almost a year, and there's no way they will allow you to use taxpayers' money to rerun it because you didn't get all the data you wanted. There's no way, unless you can claim that you will get a Nobel Prize. Even then, the price tag is huge. So the way you would typically do this, so what we have here is a data set. We don't need to discuss so much the data set. And here I plugged in the various functions. This is the R2 score, the mean square error, which we use to evaluate the quality of the model. I'm reading a comma-separated value file. So the data are given columns separated by commas. And this is a format which many of you have seen. So who has never seen that format? Okay, excellent. So this is, and in pandas, it's very easy to actually read that in. It's underscore CSV. And then you can, again, reorder everything in terms of density. In this case, this is energy. You don't need to think so much about the physics here. But I'm making a design matrix again, a polynomial fit. And my polynomial fit now is a function of the intercept. Next week, we are going to see how we can get rid of the intercept in the fit and why we could think of getting rid of it. Scikit-learn, for instance, when you compare your code with scikit-learn, you will notice that scikit-learn actually takes away the intercept by default. So if you're comparing this model with scikit-learn, you will get differences. So the scikit-learn does actually that by default, but here we keep it. So this is not often the best thing to do. And then I'm just making a polynomial where I don't have the powers of 2, 3, 4, and so on, but slightly different powers. But the thing which is important for us now is actually to look at this function, which is called train test. So this is a function which you have in scikit-learn when you're setting up the data. So what it does, it splits your data. You can see now there is an input called test size 0.2, so 20%. So it takes your data and splits it into 80% for the training and 20% for test. Now, in this specific case, there's actually no need for doing that because I could actually regenerate this data. But if you have a theory calculation where you take weeks to generate the data, then clearly splitting between test and training becomes more interesting. So this function here is also a function which interfaces with TensorFlow, PyTorch, and many of the other machine learning libraries. So one of the nice things with the scikit-learn is that it actually can be used as a kind of basic tool for more advanced deep learning methods. So the functions here returns then an array which contains your data X, the matrix which you put up. So 80%, it splits them randomly. And then, so if you rerun this, you may get a slightly different fit because it does a random shuffling of your data. And then it gives back the training data and the test data. So when you then are training everything, this is when you set up the parameter beta. Then you perform the fit here. So you have the only the training data. So keep that in mind. It's only the training data which goes into finding the parameters beta. So this is ordinary least squares. Then, in this case here, I make now a y tilde, which now contains my training data. So I'm now looking at the quality of the trained model on the data I've chosen for training. So this should give me a pretty good fit, right? Then, if you look down a little bit, the interesting quantity is actually not this one. This is just a way to see whether the training has gone well. But then the important quantity, and this is a quantity you are going to use when you make the comparison, is actually this line. So this is where you take the test data, which has not been touched upon the training, and multiply that with the parameter beta. And then clearly you can calculate the R2 with the y-test and the prediction. And then you write the test MSE and then the training mean squared error. So let's see what happens here. So you can typically see now that the training mean squared error is much better than the test mean squared error. You see that? So these are typical situations which you will encounter when you're making the training of a model. So sometimes you can get a very good training and test mean squared error. In other cases, you will actually get an excellent mean squared error for the training and a poor one for the test. But what this tells you, when you look at this pretty large value for the training, it's a bit too large. So you would obviously like to have it at least 0.1 something. So that means that my model needs improvements. So even at the training level, I'm not doing too well. So that's a clear flag that I should think of making a better model. Okay, so this was a little bit about things which we need to include in our codes and need to think of. And when we start next week, we are going to look at both statistical properties and also how to avoid calculating matrices, inverses of matrices, which actually don't have an inverse. Now, what I thought of doing now is to enter some statistics definitions and just remind you of the basic properties of statistics. However, I see now that we are just 8 minutes left, and it's always not so good to begin with a new topic. So what I would propose now is, instead of me beginning with a totally new topic, that we just stop here. Is that okay? So I'm actually giving you 8 minutes of your life, but I'm going to take them back again. Sorry for that. I don't like to begin with a totally new topic and just do 5 minutes, and then, because everybody would have forgotten it. So I hope you don't mind if we stop a little bit earlier. It's not because I don't want to be with you, but I don't want to start with a new topic. Okay, guys. Have a good weekend. So for those of you online, we're going to stop here, and then we begin with the new topics next week. Best wishes for the weekend to all of you.